Before there was any star in the sky, before light itself existed, there was a silence that was not sound, a darkness that was not darkness. There was nothing. But even that word, nothing, fails to capture what it truly means to lack time, space, energy, or matter. What existed before the universe cannot be described by the laws that govern reality today. For even time, as we understand it, had a beginning. Before that beginning, there were no seconds to count, no distances to measure. There were no vibrating particles, no pulsing fields. There wasn't even a vacuum, only a state that physics still struggles to comprehend, a pre-universe where perhaps only possibilities lay dormant. Physicists call this moment T0, time zero, the absolute threshold between non-being and being. It is the most challenging instant in modern cosmology. No equation is capable of precisely describing what came before the Big Bang. Not because we lack data, but because the very concepts of before and time become meaningless. Einstein's relativity tells us that time and space are interwoven, the so-called fabric of space-time, and that fabric only began to exist with the universe itself. This means asking what was before the Big Bang is like asking what exists north of the North Pole. The question, though intuitive, loses meaning when confronted with the structure of reality. And yet, bold theories abound. Some propose that our universe is merely a bubble within an infinite multiverse, where universes are born and die like waves in an eternal cosmic ocean. Others suggest the Big Bang was simply the transition from an earlier phase of the universe, like a collapse followed by a rebirth, the so-called Big Bounce. There are even hypotheses involving quantum fluctuations of the absolute vacuum, where reality itself may emerge spontaneously from a point of instability. But all of this remains theoretical speculation, fueled by advanced mathematics and the daring of human thought. What is most extraordinary, however, is that this initial instant, this indescribable moment, gave birth to everything we know. Every galaxy, every planet, every atom in our body was shaped by the consequences of that first breath of the universe. What was nothing became everything. Silence became vibration. Emptiness became light. And even if we never fully understand what came before time, the very fact that we are here trying to comprehend it is a testament to the greatness of what emerged from the invisible. Every heartbeat, every ray of sunlight, every particle that composes us is an inheritance from that absolute first moment, from the birth of existence itself. Faced with this mystery, perhaps the most important question is not what was before, but why does something exist instead of nothing? This question, both philosophical and scientific, remains unanswered, and perhaps it never will be. But as telescopes scan the skies for clues, and physicists dive into equations that try to unite the infinitely large with the infinitely small, we remain fascinated. Because understanding the absolute beginning is not just about knowing the universe. It is in some way an attempt to comprehend the miracle of being alive within it. In an unimaginably brief instant, around 14.8 billion years ago, everything that would ever exist, matter, energy, space, and time, emerged from an infinitely dense and hot point. This event, known as the Big Bang, was not an explosion in space, but rather an expansion of space itself. There was no sound, no light at the beginning, only the sudden and colossal release of energy that began to push the boundaries of reality in all directions. The universe, once non-existent, began its journey not in one place, but everywhere at once, since there was no outside from which it could expand. During the first trillionths of a second, the universe was smaller than an atom and hotter than any star that will ever exist. Temperatures trillions of times higher than the core of the sun made it impossible for any stable form of matter to exist. What filled the cosmos was a dense and furious broth of fundamental particles. Quarks, leptons, photons, all emerging, colliding, annihilating, and recombining every fraction of a second. But the most extraordinary thing is that, even in this seething chaos, the laws of physics were already at work. The fundamental constants, like the speed of light, gravity, and the nuclear force, emerged almost instantly, shaping the behavior of everything that would follow. Next came cosmic inflation, a phase of exponential expansion that lasted less than the blink of an eye but multiplied the size of the universe many times over in almost no time. This inflation smoothed out the geometry of the cosmos, eliminated irregularities, and planted the seeds of galaxies, tiny quantum fluctuations magnified to cosmic scales. It is one of the most enigmatic and crucial moments in the history of the universe, as it determined the very topography of what we now see in the skies. Space-time was stretched like fabric under tension, and on this stretched surface, everything began to gain shape, order, and complexity. As inflation ceased, the universe began to expand in a more gradual way, still incredibly fast, but now under the known laws of physics. The temperature started to drop, allowing the first interactions between particles to take place. The universe then entered a new stage, the era of radiation domination. In this phase, light was so intense and abundant that it kept matter trapped in a plasma state. Photons constantly collided with free electrons, making the cosmos opaque, as if wrapped in a glowing fog. It was still a universe without stars, without atoms, but already with a promising future. This inaugural instant does not merely explain the origin of the universe, it is the foundation of all existence, from the dust beneath our feet to the oceans on Mars, from the light of the stars to the chemistry of life. Everything connects back to that moment of expansion. Time itself, which we now perceive as continuous, was born there. Every second we live is a direct consequence of that first fraction of a second. And though the term Big Bang evokes an explosion, it is, in truth, the symbol of the beginning of complexity, the birth of a universe that from almost nothing gave rise to everything. Even today, billions of years later, the universe continues to expand. Galaxies drift away from one another, space stretches between them, and the echo of the Big Bang can still be detected by modern instruments, in the form of the cosmic microwave background radiation, a fossil signature of the cosmos's infancy. It is the silent whisper of the beginning of everything, traveling across the entire universe as a persistent reminder that once there was an instant when it all began. And to understand that instant is to try to touch the deepest point of existence. Right after the initial instant of the Big Bang, the universe underwent a phase of growth so rapid and so extreme that it completely defies our common sense. Cosmic inflation. In less than a minuscule fraction of a second, about a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor greater than any number the human mind can visualize. It wasn't a normal explosion, nor a gradual growth. It was an expansion of the very fabric of space-time, faster than the speed of light. Something allowed not because anything traveled at that speed, but because space itself stretched, carrying everything with it like a balloon inflating in all directions. This inflationary phase is one of the most elegant and at the same time most enigmatic ideas in modern cosmology. It was proposed to solve a series of problems that scientists faced when studying the observable universe. Why does the cosmos appear so uniform in all directions? Why is it so flat? And how could tiny fluctuations in energy have given rise to all the galaxies, stars, and planets? Inflation answers all of this with a single powerful concept. By stretching the universe exponentially, it erased wrinkles, smoothed out irregularities, and amplified tiny quantum variations to cosmic scales. The result? A vast uniform universe with slight imperfections, exactly what we observe. During this inflation, something called the inflaton field would have dominated all the energy in the universe. This field, still theoretical, would be a special kind of vacuum energy, capable of making space expand with incomprehensible force. And when this field collapsed, like a spring snapping back to its resting state, it released all the energy needed to heat the universe and produce fundamental particles. It's as if the universe stretched to its limit and, upon relaxing, unleashed the energy for everything that would come next. Matter, light, fundamental forces. Everything began there, dancing under the rules of the physics we know today. Cosmic inflation also introduced an essential ingredient for the formation of structure in the universe: quantum fluctuations. These tiny variations in density and energy, which naturally occur at subatomic scales, were inflated to colossal sizes. And these variations, though minute, became the seeds of galaxies, stars, and even planets like Earth. It's astonishing to think that the entire structure of the cosmos, including the human body, has its roots in small uncertainties of the primordial vacuum, magnified by an almost inconceivable physical process. Even though it's such a powerful idea, Inflation is still a hypothesis under refinement, but it gains strength with every new piece of data scientists collect from the depths of the sky. Maps of the cosmic microwave background reveal precisely the kind of structure inflation would predict. Areas slightly warmer or cooler, arranged in a way that could only have emerged from a universe stretched almost instantaneously. It's as if the night sky holds in its texture the fingerprint of the universe's infancy, and that fingerprint, subtle and silent, continues to tell us a story as ancient as time itself. The universe that now seems immense and complex to us was born from the broken symmetry of a boiling vacuum. Inflation is not merely a past event. It shaped everything we are. Every shining star, every living cell, every human thought, all have roots in that unheard-of expansion. And understanding inflation is to recognize that the vastness of the universe is not an accident, but the result of a precise dance between energy, space, and time, which began long before matter, light, or consciousness ever existed. With the end of cosmic inflation and the collapse of the inflaton field, the universe became saturated with such intense energy that there were no structures, no atoms, no free light, only a boiling ocean of fundamental particles. This era is known as the Epoch of the primordial soup, a hyperdense, opaque, and incredibly hot state where everything that exists today was present in its most basic and elementary form. Quarks, gluons, leptons, and photons danced in a chaotic ballet, colliding and recombining every millionth of a second, as if reality were being crushed, rearranged, and fused constantly. Quarks, too small to be seen even by the most powerful particle accelerators, are the building blocks of protons and neutrons. In that primordial broth, they existed freely, not grouped as they are today within atomic nuclei. They moved in all directions, pushed by the immeasurable thermal energy that filled every cubic centimeter of the universe. Alongside them, gluons acted as mediators of the strong force, the force that would later bind quarks together in atomic nuclei. But at that early stage, the force was still a field of free and relentless action, without defined forms or organized structures. This soup was also inhabited by leptons, such as electrons, which moved aimlessly between quarks and gluons, and biophotons are particles of light that at that stage could not travel freely. They were trapped in constant collisions with the other particles. The universe, still opaque and searing hot, was a place where light had no clear path. Everything was in constant interaction, and every point in space was a tumult of energy and motion. Even so, beneath all this chaos, the mathematical order of the laws of physics was already operating with precision. As the universe expanded, it also cooled down, and as the temperature dropped, interactions between particles began to change. By 10 microseconds after the Big Bang, the energy was already low enough for quarks to bind into triplets, forming the first hadrons, such as protons and neutrons. It was as if the universe were finding stability for the first time, moving from an amorphous soup toward the formation of the first stable structures. These hadrons would become the bricks of future atomic nuclei, the seeds of matter as we know it. Soon after, during the first seconds, the process of matter-antimatter annihilation took place. For every particle created in the universe, its opposite charge counterpart, antimatter, was also born. However, for reasons still not fully understood, ordinary matter won that battle, leaving behind a slight excess that would go on to form everything we see: stars, planets, galaxies, and even ourselves. If the balance between matter and antimatter had been perfect, nothing but photons would have remained. The fact that there is more matter than antimatter is one of the most crucial and mysterious coincidences of existence. With continued cooling, the universe transitioned from the era of free particles to a new phase, where nuclei and electrons would begin to combine. But at this stage it was still dark, dense, and opaque. And even so, it was there, in the fury of absolute heat, that the essential ingredients of matter were born, the invisible skeleton of everything that would one day take form. Understanding this primordial soup is to dive into the origin of who we are. For Bach, every atom in our body was once a stray fragment in that ocean of energy, waiting for the right moment to connect, organize, and compose the great cosmic symphony of existence. About 3 minutes after the Big Bang, The universe was still a cauldron of expansion and cooling, but it had already cooled enough to allow the formation of the first atomic nuclei. This phase, known as primordial nucleosynthesis, was a moment of silent and profound transformation. Protons and neutrons, now free from the energetic soup of the earliest moments, began to group together, bound by the strong nuclear force, forming the nuclei of the two lightest and most fundamental elements, hydrogen and helium. The universe was slowly shifting from a sea of free particles to an ordered tapestry of elemental matter. Hydrogen, made of a single proton, was the first and most abundant to appear. It formed almost immediately after the era of fundamental particles came to an end. It is the simplest and yet most essential element. Even today, more than 75% of the universe's baryonic matter is composed of hydrogen. Helium, in turn, required a slightly more complex condition, 2 protons and 2 neutrons in a stable union, and as soon as the density and temperature allowed, these nuclei also formed in large quantities, approximately 25% of the visible matter in the universe. Today consists of helium. Other elements like lithium and deuterium emerged in much smaller amounts, minor notes in a symphony dominated by 2 protagonists. But there were still no complete atoms, only nuclei. Electrons, though abundant, could not bind to the nuclei due to the still high temperature and density. The radiation was so intense that any attempt to form an atom was immediately undone. It was like trying to light a candle in the middle of a hurricane. This condition lasted for hundreds of thousands of years. During that period, the universe was a mass of ionized plasma, an environment where matter and light were intrinsically linked, preventing photons from traveling freely. It was a cosmos without transparency, without visible light, an opaque fog of energetic particles. Only feet around 380,000 years after the Big Bang did the universe cool enough for electrons to finally bind to nuclei, forming the first stable atoms. This moment is known as the epoch of recombination, not because atoms had previously broken apart, but because electrons now recombined with nuclei, creating for the first time complete atomic structures. With hydrogen and helium atoms now formed, photons were no longer constantly absorbed and re-emitted by charged particles, and they could finally travel freely through space. This liberation of light is known as the birth of the cosmic microwave background radiation, the universe's first glow, still visible today as a cold and faint mist that permeates all of space. It is an ancient portrait of the universe's infancy, frozen in time, revealing that from very early on, the seeds of structure were already sown. The slightly denser regions would attract more matter, while the less dense would remain nearly empty. Thus began the long process that billions of years later would give rise to stars, galaxies, and eventually life. The birth of atoms was more than a physical transition. It was the first moment when the universe became recognizably real. For the first time, matter gained stable form. For the first time, light could travel, and from that instant on, the universe carried within it the fundamental conditions for complexity, opening the path to everything that would follow. Structure, chemistry, biology, consciousness. Everything begins with the simplicity of hydrogen and helium. Everything begins with atoms drifting silently in the dark as time passes and the universe matures. After the birth of the first atoms, the universe entered a deep and silent period known as the Cosmic Dark Ages, a mysterious and extended interval in the history of the cosmos, lasting approximately 100 to 200 million years, during which there were no stars, no galaxies, and no visible light. Space, although already filled with hydrogen and helium atoms, remained plunged in total darkness. The cosmic microwave background had already been emitted, but its light had cooled to the point of becoming invisible to human eyes. It was a dense, cold, and calm universe, the closest reality has ever come to absolute silence. During this era, atoms floated through the newly expanded space. Gravitational forces slowly began to operate in the background of the vast darkness. Small density fluctuations, planted during inflation, now acted as gravitational seeds. In those slightly denser regions, atoms began to gather, pulling one another with the patience of billions of years. These concentrations would gradually grow until they became dense enough to collapse under their own weight, initiating the formation of the first stars. But this process was slow, silent, and invisible. The universe was a stage without lighting, where the main characters were still being shaped behind the curtains of gravity. During this time, the average temperature of the universe steadily decreased. The expansion of space diluted energy and stretched the waves of residual radiation. Particle collisions became increasingly rare, and the universe grew progressively colder and more rarefied. Yet this darkness was not sterile. It was an invisible period of preparation, where physics worked with patience and precision. In the densest regions, atoms began to form clouds, vast and cold, composed primarily of hydrogen. These clouds would become the nurseries of the first stars. But before that could happen, the cosmos had to wait, and wait in silence. One of the most fascinating features of this era is that although the universe was already filled with matter and governed by complex laws, nothing was visible. Light, as we know it, did not yet exist. There were no stars to shine, no galaxies to emit radiation, only a diffuse and almost perfect darkness. It was the darkest moment in cosmic history, but also one of the most important, because, paradoxically, it was in the silence that structure organized itself. It was in the darkness that the universe began to lay the foundations for what would come next. Light, heat, heavier elements, complexity. As gravity continued its tireless work, some regions grew increasingly dense, initiating gravitational collapses that would raise the temperature within the clouds. The hydrogen gas, when compressed, began to heat up. And one day, in some remote corner of the cosmos, the temperature would rise high enough to trigger a nuclear fusion reaction, the birth of the first star. With that, the Dark Age would come to an end. But before that, the universe spent millions of years as a vast invisible ocean where there was no form, no light, only the silent promise of all that would one day be. Understanding the Dark Ages is realizing that the absence of light is not the absence of meaning. On the contrary, it was in this dark and seemingly inert period that the universe matured. It is a reminder that the invisible often prepares the way for the spectacular. Silence is not emptiness, but gestation. And in the case of the cosmos, it was Isita, from the deepest darkness, that the first spark of light was born, a light that would change everything forever. After hundreds of millions of years immersed in total darkness, the universe finally began to ignite its first points of light. Those silent clouds of hydrogen, formed during the Dark Ages, had been pulled by gravity to the point of collapsing in on themselves. Amid increasing pressure and gradually rising internal temperatures within these clouds, a critical threshold was finally reached. Hydrogen atoms began to fuse, releasing energy in the form of light and heat. Thus were born the first stars, primordial giants, extremely massive, hot and luminous, which for the first time lit up the universe with nuclear fire. These first stars, known as population 3 stars, were unlike any we see today. Composed solely of hydrogen and helium, the only elements available at the time, they contained no metals or heavy elements. This gave them unique properties. They were much larger, often hundreds of times more massive than the Sun, and had extremely short lifespans. They burned through their fuel quickly in just a few million years, collapsing into titanic supernovae that left behind black holes or neutron stars. These explosions not only destroyed the stars, but also created new elements and scattered them through space, initiating the cosmic alchemy that would shape everything to come. With the birth of these primitive stars, the universe entered a new phase, the epoch of reionization. The intense ultraviolet radiation emitted by these stars began to break apart neutral hydrogen atoms, separating their electrons from their protons. This reionization process restored transparency to the cosmos, allowing light to propagate freely across great distances. For the first time since recombination, the universe became permeable to radiation again. Light could travel, encounter obstacles, reflect heat, and transform. Absolute darkness had been conquered. The cosmos had finally become visible. These early stars did not emerge in isolation. As gravity drew gas clouds together, it also caused many stars to form in close regions, giving rise to the first stellar clusters. Over time, these clusters would merge and organize into proto-galaxies, which would grow as the ages progressed. But in the beginning, the glow of the first stars was like matches struck in a dark forest, brief, intense, solitary. And even so, they were the ones that broke the universal silence and heralded a new era of light and complexity. The emergence of light in the universe was not merely a physical spectacle. It was a profound cosmic turning point, where matter, until then invisible and dispersed, began to reveal its presence. Gravity and nuclear fusion had found a way to transform simple atoms into sources of radiation, and with that, information began to travel through space. Light carries data about temperature, composition, distance. Through it, the universe began to tell its story, even if silently. And it is this light, emitted by stars billions of years ago, that still reaches our telescopes today, allowing us to see the past with the eyes of the present. Every star that shines in the night sky is a direct heir of those pioneers. Every drop of gold, iron, or carbon in our bodies is descended from their explosions. When we look up, we do not just see points of light. We see the trace of the moment when that the universe awoke from darkness and revealed itself as an expanding tapestry, rich in heat, energy, and beauty. The light that broke the void did not merely illuminate space. It inaugurated the path of consciousness, of observation, of life. And from that moment on, the cosmos was never the same again. The first stars, gigantic and unstable, lived brief lives, but ones of intense productivity. Within them, under unimaginable temperatures and pressures, these stars began the process of nuclear fusion, fusing hydrogen atoms into helium, and later helium into progressively heavier elements such as carbon, oxygen, neon, and silicon. This fusion generated an outward force, radiation, which counterbalanced the inward pull of gravity. It was a battle of titans inside every stellar core, but that balance was temporary. Once the nuclear fuel was depleted, gravity ultimately triumphed, and the star collapsed violently, unleashing one of the most destructive and creative forces in the cosmos, the Theta supernova. Supernovae are not merely cosmic spectacles of destruction, they are also alchemical nurseries, furnaces where the universe manufactures its metals and complex elements. It is during the collapse and explosion of a massive star that enough energy is released to form elements heavier than iron, such as gold, silver, uranium, and lead. These elements cannot be formed during ordinary stellar fusion, as they require more energy than they produce. But the fury of a supernova changes everything. The pressures and temperatures reach such extreme levels that matter is forced into denser, heavier forms, rich in chemical potential. It is there that the periodic table gains its full body. The explosion of a supernova spreads these newly created elements across vast regions of interstellar space. Each shockwave carries with it the product of billions of years of stellar evolution. These enriched clouds of gas and dust become raw material for new generations of stars and planets. In this way, the universe is continually recycled. A star dies, but with it, new possibilities are born. The gas clouds that once contained only hydrogen and helium are now infused with carbon, iron, nitrogen, sulfur, and hundreds of other ingredients that will one day form mountains, oceans, atmospheres, and eventually living organisms. It is fascinating to realize that every atom of calcium in our bones, every atom of iron in our blood, and every atom of phosphorus in our brains was once inside a dead star billions of years ago. We are literally made of stardust. The phrase "we are made of stars" is not a poetic metaphor. It is a physical truth, measurable and repeatedly confirmed by spectroscopic analyses of cosmic elements. Life, chemistry, and consciousness all were made possible by earlier generations of stars that in dying scattered their contents like cosmic seeds. Beyond supernovae, there are also neutron stars and their collisions, events even rarer but incredibly fertile in heavy elements. These collisions, recently observed thanks to gravitational wave detectors, have proven to be responsible for much of the gold and platinum in the universe. They are cataclysmic encounters between stellar corpses that, upon merging, produce not only light, but also dense precious matter. These are the final furnaces, the last chapters of cosmic alchemy. Thus, the universe evolved from a simple stage composed of a few light elements to a cosmic laboratory. where stars fuse, shape, and distribute the fundamental building blocks of complexity. Supernovae not only illuminate the sky for brief moments, with a brilliance surpassing that of entire galaxies, they sow the future, creating the conditions for planets with atmospheres, oceans, and perhaps in rare cases, even intelligent life. The universe became more interesting, more colorful, more fertile, and it all began with the collapse of giants. From the violent end of a star was born the beginning of chemistry, biology, and thought. With the universe already illuminated by the first stars and enriched by the elements forged in their explosive deaths, matter began to gather into something even greater, the first galaxies. This process did not happen suddenly. It was the result of the millions of years of gravitational interaction, where small density fluctuations in space became gravitational wells, pulling gas, dust, and newborn stars into centers of condensation. These regions formed the first stellar clusters, which, bound by gravity, grew, collided, and merged until they reached galactic dimensions. Cosmic darkness was beginning to be sculpted into majestic structures. These early galaxies were very different from the ones we see today. They were smaller, more chaotic and denser, filled with young and extremely bright stars. The light we see today from these primitive galaxies has traveled for more than 13 billion years, and only recently have we been able to detect it using ultra-advanced telescopes like the James Webb. These observations confirm that the first galaxies emerged around 300 to 400 million years after the Big Bang, a short time in cosmic terms, yet already demonstrating the universe's ability to organize itself on immense scales. Matter was no longer just scattered gas and dust, but islands of light and gravity sailing the ocean of space-time. As they grew, these galaxies became more structured, acquiring spiral, elliptical, or irregular shapes. Spiral galaxies, like our Milky Way, displayed curved arms rotating around a dense core. Elliptical galaxies were more rounded, composed mostly of old stars and little gas. Irregular galaxies, on the other hand, were distorted by gravitational interactions, collisions, and mergers. This growth process was not peaceful. Galaxies collided, cannibalized, and absorbed one another, blending their stars, black holes, and histories in a whirlwind of constant transformation. At the heart of nearly every galaxy, scientists discovered a mysterious entity, a supermassive black hole, with masses reaching billions of times that of the Sun. These extreme objects appear to have grown alongside the galaxies themselves, feeding on nearby gas, dust, and stars. When active, they release jets of radiation and matter that can span thousands of light years, affecting the pace of star formation in surrounding regions. They are at once silent predators and invisible sculptors of galactic structure. The link between the growth of galaxies and the development of these black holes is one of the great mysteries of modern astrophysics. Over time, galaxies began to gather into even larger structures, galaxy clusters and superclusters. These immense cosmic networks, connected by filaments of dark matter, form what is now known as the cosmic web, a gigantic and tangled structure that stretches across billions of light years, composed of filaments, voids, and gravitational nodes. Seen on a large scale, this web resembles the structure of a neural network or cosmic foam, with galaxies grouped along filaments and vast empty spaces between them. It is the largest known pattern in the universe, born from the tiny quantum fluctuations of the early cosmos, magnified by billions of years of gravity. Each galaxy contains billions or trillions of stars, hundreds of billions of planets, countless comets, asteroids, nebulae, and still unknown forms of matter, and all of it moves, transforms, and interacts. Galaxies are cosmic cities, where physics writes its story with brilliance, motion, and depth. They are beacons of light that cross time and tell tales of birth, transformation, and rebirth. Studying their formation is to study how the universe evolved from chaos and diffusion to become a structured mosaic filled with order and potential for life. The formation of the first galaxies was the essential step for the cosmos to cease being merely a vast darkness with scattered points of light. Now, matter was assembling into complex and enduring systems, capable of generating stellar cycles, planets, and one day, even consciousness. When we look at the sky and see a distant galaxy, we are observing a preserved memory, a testament to how the universe learned to organize itself and nurture complexity from the simple. And in that silent gravitational dance, the structures that would one day become the stage for life were born. At the heart of the young universe, amid the chaos of forming galaxies, stars, and elemental structures, even more enigmatic and silent entities emerged, the primordial black holes. Unlike black holes formed from the collapse of stars, these extreme objects may have arisen in the very first moments after the Big Bang, when intense density fluctuations collapsed directly upon themselves, concentrating so much mass into such a small volume that not even light could escape. They are hypothetical objects, yet intensely studied, as they may hold the keys to ancient secrets of the universe, such as the nature of dark matter, the origin of galaxies, and the behavior of space-time under the most extreme conditions. If they exist, these primordial black holes would have extremely varied masses. Some could be smaller than a mountain, compressed into microscopic volumes. Others could have masses equivalent to planets or even entire stars. Most remarkably, because they don't depend on the death of stars, they could have been born within the first seconds of the universe, even before the formation of atoms. This makes them natural candidates to explain the hidden aspects of the cosmos. Some theorists suggest they could constitute a significant portion of dark matter, the invisible substance that permeates the universe and influences the rotation of galaxies, yet has never been directly detected. These objects are also valuable for another reason. They serve as natural laboratories for studying the extreme laws of physics. The boundary of a black hole, known as the event horizon, marks the limit where gravity is so intense that even light cannot escape. Anything that crosses it vanishes forever, becoming inaccessible to our knowledge. At the center lies a singularity, a point of infinite density where the known laws of physics break down. It is the endpoint of the geometry of space-time, where time and space collapse, and concepts such as past and future become irrelevant. If primordial black holes exist in the billions, scattered throughout the universe, they may have played a crucial role in the formation of cosmic structures. By pulling in surrounding matter, they could have served as condensation centers for the first galaxies. In other words, the great cosmic cities of stars and planets may have begun around these silent and invisible bodies, long before the light of the first stars appeared. This idea revolutionizes our understanding of the universe's architecture, suggesting that the invisible, not the visible, may have laid the foundation for everything we see. With the advancement of technology, gravitational wave detectors like LIGO and Virgo have begun capturing signals from black hole mergers. Some of these signals involve objects with unusual masses that don't match traditional models of stellar evolution. This raises the possibility that we are hearing echoes of primordial black hole mergers, ancient, silent encounters between bodies formed long before any star. These signals are like whispers from the deep past, and each detection invites us to reconsider what we think we know about the beginning of reality. Studying primordial black holes is more than a search for dark and exotic objects. It is a quest for the gravitational memory of the universe, etched into the curves of space and the echoes of time. They are entities that defy logic, ignore light, and embrace silence, and yet they may be the hidden pillars of cosmic history. They remind us that the universe is not made only of stars that shine, but also of abysses that bend time and conceal secrets, sealed doors to dimensions of existence we do not yet understand, but may one day glimpse in the oldest folds of the sky. In the heart of the cosmic ocean, filled with young galaxies and primitive stars, a structure began to emerge with unique and promising characteristics. The Milky Way, the cosmic home where, billions of years later, Earth, life, and consciousness would arise. Its formation was a slow and turbulent process, marked by mergers, collisions, and absorptions of smaller galaxies. It is estimated to have begun forming around 5 billion years ago, shortly after the Big Bang, as a cluster of stars and gas clouds with no defined shape. Over billions of years, these primordial blocks gradually organized themselves, guided by gravity, into the magnificent spiral disk that now hosts hundreds of billions of stars. At first, the Milky Way was merely a dispersed collection of smaller proto-galaxies, all orbiting around centers of mass and approaching one another through mutual gravitational forces. With each collision and merger, Its mass increased, its structure took shape, and its rotation intensified. Over time, this chaotic collection acquired a spiral shape, a flat disk with curved arms, slowly rotating around a dense core. The spiral arms began to act as interstellar nurseries, regions of compressed gas where new stars were born at a steady rate, like silent fireworks lighting up the darkness between eras. The center of the Milky Way, known as the galactic bulge, is an ancient and dense region composed mainly of old metal-poor stars. At the core of this bulge lies one of the most mysterious and powerful objects in the galaxy, Sagittarius A, a supermassive black hole roughly 4 million times the mass of the Sun. This invisible colossus exerts gravitational influence over the entire galactic system and may have played a decisive role in organizing the Milky Way into its current form. Though it remains in near-total silence, it is constantly pulling matter around it, influencing the motion of stars and gas clouds across tens of thousands of light-years. The Milky Way is composed of four main structural components: the central bulge, the thin disk, where the solar system is located, the thick disk, made of older and more dispersed stars, and the galactic halo, a spherical and diffuse region that surrounds the entire galaxy, filled with globular cluster and, it is believed, dark matter. This dark matter is invisible, emits no light, and does not directly interact with ordinary matter, but its presence is detected through its gravity. It appears to be responsible for maintaining the cohesion and rotation of the galaxy at speeds that would be physically impossible without it. It is an invisible skeleton supporting everything we know. Today, the Milky Way continues to grow and evolve. For instance, it is currently absorbing nearby dwarf galaxies, such as the Sagittarius galaxy, which is slowly being torn apart by gravitational tides. And in the distant future, in about 4 billion years, the Milky Way is expected to collide with the Andromeda galaxy, forming a new giant galaxy, a monumental merger that will completely transform the night sky. Despite the enormity of this collision, the distances between stars are so vast that most stellar systems will not collide directly, though their orbits will be altered and redistributed into a new pattern of order. Thinking about the Milky Way is to think in terms of scale, time, and belonging. We are a small part of a stellar system called the solar system, which is just one among hundreds of billions of systems within the galaxy. Our Sun is located about 26,000 light-years from the center, in a spiral arm called the Orion Arm, a relatively calm and stable neighborhood which may have been crucial for the emergence of life. Everything we know, Earth, the Moon, the planets, every atom in our bodies, was born and shaped within this galaxy, a direct heir of ancient explosions, dust clouds, gravitational fields, and invisible tides of dark matter. The Milky Way is not merely the backdrop of the night sky. It is our cosmic home, a monument of billions of years, full of stories written in stars, trails of comets, and silent pulses of radiation. To know it is to remember that life did not arise in isolation, but as part of a much older and vaster process. Every star that twinkles in the celestial dome is a point in its structure, and each of us, gazing at that sky, is looking at the roots of our own origin, a spiral of dust, light, and time that welcomed and shaped us about 6 billion years ago. In a quiet region of a spiral arm of the Milky Way, a giant interstellar cloud of gas and dust began to undergo gravitational disturbances. It may have been the natural collapse of the cloud itself, or perhaps a shockwave from a nearby supernova. Either way, the result was the same. The cloud slowly began to contract under its own gravity. As it shrank, it spun faster and faster, flattening into a rotating disk, dense at the center and diffuse at the edges. This rotating disk of matter would, over time and heat, give rise to a new stellar system, the solar system. At the center of the collapsing cloud, the material became so dense and hot that it triggered nuclear fusion, the process that transforms hydrogen into helium, releasing immense amounts of energy. Thus was born the Sun, a G-type star that would convert its mass into light and heat for billions of years. With its dominant mass, the Sun began to influence all the surrounding material. Its radiation pushed the lighter gases outward, while heavier elements accumulated in the inner regions. The protoplanetary disk, still rotating, became the nursery of the planets, moons, asteroids, and comets we know today. The particles of dust and minerals within the disk began to clump together, first into grains, then into rocks, then into increasingly larger bodies called planetesimals. These planetesimals, through collisions and mergers over millions of years, gave rise to two protoplanets, still forming planetary cores covered in lava and bombarded by cosmic debris. The intense radiation from the newborn sun prevented light gases from accumulating in the closer planets. Thus, Mercury, Venus, Earth, and Mars became small and rocky, while in the outer regions planets could retain large envelopes of gas, giving rise to the fast gas giants: Jupiter, Saturn, Uranus, and Neptune. Jupiter, the largest planet in the system, played a critical role. Its colossal gravity disrupted the formation of other bodies and prevented a fifth rocky planet from forming between Mars and itself. Instead, that region became filled with debris and rocks, now known as the asteroid belt. At the same time, on the distant edges of the system beyond Neptune, thousands of icy bodies formed, including Pluto and even more remote objects that today make up the Kuiper belt and the Oort clouding, ancient reservoirs of comets that occasionally visit the inner system with their bright tails. The formation of the solar system was far from peaceful. For hundreds of millions of years, the still-forming planets collided with wandering objects during a period of intense bombardment known as the Late Heavy Bombardment. During this time, Earth was struck by a Mars-sized body, a colossal impact that ejected a massive amount of debris into space. This debris quickly gathered, forming the Moon, which began to orbit the Earth and influence its rhythms from that moment on. The Moon's presence, in fact, was crucial for stabilizing Earth's axial tilt and ensuring regular tides, conditions that would later prove essential for the emergence of life. Meanwhile, the interiors of the planets began to differentiate. Denser materials sank to form metallic cores, while lighter ones rose, creating mantles and crusts. Earth, in particular, developed a solid crust, a protective magnetic field, and an atmosphere rich in water vapor. This combination would later allow for liquid oceans, stable climates, and organic molecules. The solar system, now in relative stability, had become a repository of cosmic diversity. Rocky and gaseous planets, moons with underground oceans, ice volcanoes, magnetic fields, auroras, and billions of smaller objects forming a mosaic that still fascinates astronomers and scientists today. Each component of the solar system is a testament to the natural process that shapes the cosmos. The sun warms and commands, the planets spin silently, maintaining near-perfect orbits. The asteroids and comets travel as relics of the primordial past. And in the midst of it all, Earth spins quietly, carrying a rare mystery: life. To look at the birth of the solar system is to realize that, even amid chaos, nature follows patterns, builds order, and plants possibilities where once there was only cosmic dust. It is to understand that everything we see in the sky, and everything we are, was born from an anonymous cloud of gas, slowly spinning in a quiet corner of the galaxy. Right after its formation, Earth was a planet radically different from the one we know today. It was a sphere in constant transformation, shaped by extreme energy and violent events. Its interior was still molten, filled with bubbling magma and fused metals. The surface was a scene of incandescent desolation, covered by oceans of lava, continuously erupting mountains, and craters opened by the constant impacts of meteors. Heat came from every direction, from the residual energy of gravitational collapse, from the relentless bombardment of asteroids, and from the radiation of radioactive elements within its core. Earth was, quite literally, a boiling furnace spinning in the darkness of space. There were no oceans or breathable atmosphere. The sky was opaque, suffocating, filled with toxic gases such as carbon dioxide, methane, ammonia, and water vapor. Sunlight barely penetrated the thick blanket of sulfurous clouds. Lightning constantly slashed the sky, fueled by electrical storms generated by heat and chemical reactions. Gravity pulled the densest elements toward the core, creating a layered internal structure: a metallic core, a viscous mantle, and a superficial crust, still fragile, cracked, and unstable. Even so, This differentiating structure would later enable the formation of tectonic plates, volcanism, and the magnetic field that still protects the planet today. During the first billion years, Earth was intensely bombarded by meteors of all sizes. Many of these impacts were catastrophic, releasing more energy than billions of nuclear bombs. It was also during this time, scientists believe, that a Mars-sized body collided with Earth, ejecting tons of material into orbit. This debris quickly aggregated, giving birth to the Moon. This satellite, beyond influencing tides and stabilizing Earth's axial tilt, also played a crucial role in Earth's evolution, reducing the intensity of later impacts and creating gravitational cycles that continue to influence climate and oceans. The origin of water, one of science's great mysteries, may have multiple sources. Part of it likely came from Earth's own interior, released through volcanic eruptions in the form of vapor. Another portion may have been delivered by comets and ice-rich asteroids, which, upon impact, deposited their contents onto the forming crust. Over time, as the surface cooled, this vapor condensed into rain, endless rain that fell for thousands of years, forming the first primitive oceans. These early seas still boiled, cut through by submerged volcanoes and deep hydrothermal vents, but they already represented the first stable liquid environment on Earth, a chemical ocean full of potential. The primitive atmosphere was hostile to life as we know it. It contained no free oxygen. It was dominated by heavy gases and violent reactions, creating an environment of abundant but unstable energy. Yet it was in this seemingly inhospitable setting that the first organic molecules began to form, born from chemical reactions triggered by lightning, solar radiation, and volcanic heat. Compounds such as amino acids and nucleotides may have formed spontaneously in shallow ponds, hot lakes, or even deep-sea hydrothermal vents. These early compounds were the fundamental building blocks of life, and Earth, despite the chaos, became a natural laboratory for chemical experiments on a planetary scale. Over time, Earth's crust stabilized. Tectonic plates began to move, creating primitive continents, mountain ranges, and ocean trenches. Volcanoes continued to play a vital role, not only by releasing gases that would enrich the atmosphere, but also by heating subterranean regions with constant energy, ideal sites for complex organic reactions. Earth had ceased to be just a molten sphere. It began to exhibit cycles of water, of heat, of elements, and with them the rhythm that would one day give rise to metabolism. It was a planet in transition, from absolute hostility to fertile possibility. To look at early Earth is to understand that life did not emerge in a serene garden, but in the midst of fury, instability, and fire. The planet went through a violent childhood, and it was precisely that violence, internal heat, cosmic impacts, aggressive chemistry, that generated the ingredients of the future. Every molecule of water in our bodies today, every grain of soil, every living cell, is a direct inheritance from that stormy past, from that incandescent planet that cooled, rained, healed its wounds, and learned to harbor life. Amid the primitive Earth, still marked by intense heat, boiling oceans, and a toxic atmosphere, emerged the first signs of something extraordinary, molecules capable of organizing, reacting, and evolving. These were not yet cells, nor organisms, but they were the very first chemical steps toward life. The ingredients were all present, and among them two elements stood out as indisputable protagonists: water, the universal solvent, and carbon, the molecular architect of biology. Together, they created the chemical stage where improbable reactions began to occur frequently enough to transform the inanimate into the animated. Liquid water, found in the newly formed oceans and in underwater hydrothermal vents, provided the ideal environment for these reactions. Its polar structure allows it to dissolve a wide variety of substances, bringing molecules close together, facilitating collisions, and enabling reactions that would otherwise be unlikely. Moreover, water acts as a thermal regulator and a transport medium for molecules. Without it, the chemistry of life would have had little chance of organizing. And more than that, the very stable presence of liquid water on Earth is the result of a rare balance between temperature, atmospheric pressure, and planetary composition, a cosmic detail that changed the fate of our world. Carbon, in turn, is the master element of complexity. With 4 electrons available for bonding, it can form chains, rings, branches, and 3-dimensional structures of great stability. It bonds easily with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the other essential elements of biochemistry. This makes it possible to form complex molecules like amino acids, lipids, sugars, and nitrogenous bases. These compounds, though simple at first glance, have the ability to react, to combine into larger structures, and even to self-organize. In laboratory experiments like the famous Miller-Urey simulation, such molecules spontaneously formed under conditions that mimic those of early Earth. In energy-rich environments, such as hot ponds, volcanic lakes, and hydrothermal vents, these organic molecules began to cluster into more complex structures. Some formed chains, others membranes. It is possible that the first prototypes of lipid membranes emerged, pouch-like structures, capable of isolating their interior from the external environment. These microcapsules may have hosted stable internal reactions, creating the embryo of the first cells. The abiotic world was beginning to develop boundaries, an interior and exterior, something essential for life. Chemistry, without intent, was building the architecture of biology. But perhaps the most mysterious and fascinating step was the emergence of molecules capable of storing and replicating information. Scientists believe that before DNA, there may have existed a world dominated by self-catalyzing RNA molecules. These molecules have the rare ability to function both as genetic material and as catalysts for chemical reactions. They can copy themselves, fold, and adapt. A primitive RNA system, working in concert with membranes and other biomolecules, may have been the first almost living system capable of evolving through natural selection, a threshold between chemistry and life. Over time, these molecular systems became more efficient, more complex, and more durable. RNA gave way to DNA, more stable and reliable. Proteins emerged as versatile tools, capable of executing specific tasks with precision. Membranes became more robust, and rudimentary metabolism, the ability to capture and convert energy, began to take shape. At some point in this improbable chain of events, a boundary was crossed. The first living cell was born, a microscopic being capable of maintaining its integrity, reproducing and evolving. And from it, the entire tree of life began its long, branching journey. To look at the origin of the molecules of life is to understand that the impossible can become inevitable when time, diversity, and energy converge. Life did not appear by magic, but through millions of tiny chemical steps, each paving the way for the next. Carbon and water, under the right conditions, became the silent craftsmen of the miracle. And the most astonishing part is knowing that the same elements that form our bones, muscles, eyes, and thoughts were already present in stardust, in ancient comets, in the searing seas of the newborn planet. Life, in the end, is chemistry endowed with memory, complexity, and the will to continue. With the emergence of the first cell, around 3.8 billion years ago, the universe had reached a new threshold. Matter had learned to organize itself persistently, to replicate, and to evolve. It was a silent but cosmic turning point. For the first time, something in the universe not only existed, but also sought to continue existing. This ancestral cell, likely a simple anaerobic unicellular form of life, began a long and uninterrupted journey that, generation after generation, would transform the planet and the very nature of what we understand as reality. What was once only chemistry was now becoming biology, history, behavior, and memory. These first organisms lived in aquatic environments, likely near underwater hydrothermal vents, where chemical energy was abundant. Without performing photosynthesis yet, they extracted energy directly from mineral reactions in a process called chemosynthesis. But over time, organisms capable of capturing sunlight and converting it into energy emerged. Cyanobacteria, true living powerhouses that changed the world. Through photosynthesis, they began to release oxygen as a byproduct, drastically altering Earth's atmospheric composition. This oxygen, initially toxic to many forms of life, would eventually become the foundation of cellular respiration and the explosion of biological complexity. With more energy available, life was able to diversify. Cells began to cluster, specialize, and form multicellular organisms. This slow and irreversible process led to increasingly complex forms: sponges, jellyfish, worms, primitive plants. Evolution, guided by natural selection, experimented with every possible form, preserving those that worked and discarding those that didn't. That's how eyes evolved. Wings emerged and brains began to form. Every adaptation, every beneficial mutation, accumulated like a musical note in a biological melody, billions of years in the making. Between 500 and 600 million years ago, during the period known as the Cambrian explosion, the diversity of life forms skyrocketed at an astonishing pace. Animals with skeletons, shells, jointed limbs, and nervous systems appeared in a geologically short time span. Gradually, the oceans became arenas of interaction, hunting, defense, and reproduction. Life had become dynamic, predatory, and sensitive. And at some point along that trajectory, the first fish emerged, followed by amphibians, reptiles, mammals, and much later, primates, humans, and the consciousness that now contemplates its cosmic past. Consciousness is perhaps the most mysterious and extraordinary phenomenon in the universe. From a scientific perspective, it emerges from the extreme complexity of neural networks, but philosophically, it represents something even deeper: the universe observing itself. Matter born from a primordial soup of particles that gathered into stars and galaxies, exploded in supernovas and formed planets, now finds itself reflected in eyes that think, feel, and question. Life is not just a natural consequence of organic chemistry. It is a rare spark that transforms existence into experience, into identity, into history. Everything we are, every cell, every thought, every breath, carries billions of years of unbroken continuity. Life has survived volcanoes, catastrophic impacts, ice ages, mass extinctions, and continental rearrangements. It persisted, adapted, and transformed. And even after countless failed attempts, it never stopped trying something new. It is this impulse, this inner force that drives us to grow, learn, communicate, care, and explore, that may be the true miracle. Life is, at its core, order emerging from chaos, meaning emerging from repetition, consciousness emerging from matter. The miracle of life lies not only in its origin, but in its continuity, in how it has remained cohesive for billions of years, crossing eras, continents, and extinctions, until arriving at beings capable of contemplating time, space, and their own fragility. When we look at the sky and think about stars, planets, and distant galaxies, we are witnessing not only the vastness of the universe, but the power of life to rise from the inanimate, to organize itself, and to ask why. Life, in its essence, is a question posed by matter to the void, and every living being is an attempt at an answer. Since the moment of the Big Bang, the universe has been in constant expansion. Galaxies drift away from each other like dots on a balloon that is slowly being inflated. For billions of years, scientists believed that this expansion, while ongoing, was being gradually slowed by gravity, as if the universe were decelerating, perhaps heading toward a future of collapse or balance. However, at the end of the 20th century, a discovery completely changed that view. By observing distant supernovae, astronomers realized that the expansion of the universe was not just continuing, it was accelerating. Something invisible, mysterious, and dominant was pushing the cosmos with a force that defied logic, the so-called dark energy. This acceleration means that galaxies are moving away from each other faster and faster, and that, over immense timescales, the universe will become a colder, darker, and lonelier place. The light from distant galaxies will eventually be so far removed that it will no longer be able to reach us. Telescopes of the future, trillions of years from now, will see a blank sky, with no trace of the cosmic past we can currently observe. This prospect, though melancholic, is a direct consequence of the physical laws that govern the geometry and energy of space-time. Expansion is inscribed in the very fabric of the universe, and nothing, as far as we know, can stop it. Dark energy, the force behind this acceleration, is perhaps the greatest mystery in modern cosmology. It is not visible, it doesn't interact with light, and its nature remains uncertain. Some scientists describe it as a property of space itself, a vacuum energy that increases as the universe expands. Others see it as an unknown force, a cosmic field that permeates everything. What we do know is that it makes up roughly 68% of all the energy in the universe. far surpassing both ordinary matter and even dark matter. In a way, it is the dynamic backdrop that dictates the destiny of the cosmos. With continued acceleration, the universe is heading toward what scientists call the Big Freeze. In this scenario, expansion never stops but becomes so extreme that stars cease to form, galaxies fall apart, and even atoms decay into isolated subatomic particles. The average temperature of the universe would drop close to absolute zero, and all usable energy would dissipate. There would be no more light, no heat, no interaction, only distant particles floating in eternal silence. It's a radically different vision from the Big Bang. Instead of an explosive birth, a disappearance through rarefaction and thermal isolation. But other possibilities remain. The universe could be unstable in its current state, and at some future point, dark energy might behave differently. In a scenario called the Big Rip, the acceleration would become so intense that not only galaxies and stars would be torn apart, but atoms and even the fabric of space-time itself would be ripped. This is a much more abrupt ending, where everything that exists is destroyed by an ever-growing, uncontrollable force. In older models, still considered by some, there's the chance of a big crunch where expansion would stop and reverse, causing the universe to collapse in on itself. However, current evidence strongly favors the model of eternal expansion. Regardless of the final outcome, one thing is certain: the universe is not static. It pulses, breathes, transforms. The idea of an unchanging cosmos was buried by modern observations, replaced by the concept of a universe in constant flux, driven by forces we have barely begun to understand. Accelerated expansion forces us to rethink our place in time and space. We are a small manifestation of complexity, born between the Big Bang and the final silence, existing in a brief window where stars still shine and atoms still organize. To think of infinite expansion is like watching a river flowing into nothingness, carrying galaxies, planets, and memories with it. A movement without borders, without a visible destination, only the certainty that everything is drifting away from everything else. And yet, in this specific moment of cosmic time, we are here, conscious, observing, measuring, asking. Perhaps the true mystery is not the end of the universe, but the fact that between the absolute beginning and the eternal dispersal, matter found a way to awaken. And it is this brief wakefulness between two infinities that makes existence so rare and so extraordinary. Few things in the universe are as mysterious as dark energy. It emits no light, reflects nothing, doesn't interact directly with ordinary matter, and yet it accounts for nearly 70% of everything that exists. It is a silent, intangible presence, yet its effects are colossal. It accelerates the expansion of the universe, modifies the geometry of space-time, and challenges some of the most fundamental laws of physics. Discovered late, dark energy didn't just alter our understanding of cosmology, it redefined the future of the cosmos. Because if matter shapes what we see, dark energy shapes where everything is going. Its existence was revealed in 1998, when two independent teams of astronomers observed Type Ia supernovae in distant galaxies. The goal was to measure the rate of the universe's expansion, expecting to confirm a slowdown caused by gravity. But they found the opposite. Those galaxies were moving away faster than predicted. This meant that expansion was accelerating, and that some invisible force was pushing everything outward. Thus, the concept of dark energy entered science not as an exotic hypothesis, but as the only viable explanation for a phenomenon already confirmed by data. But what exactly is dark energy? That remains the great question. One of the most accepted theories is that it's a property of the vacuum itself, a cosmological constant that arises naturally in Einstein's equations of general relativity. In this view, empty space is not truly empty. It has intrinsic energy, and that energy exerts a negative pressure, a force that drives space itself to expand. As the universe grows, more space is created, and with it, more dark energy. This creates a self-sustaining cycle of expansion, becoming increasingly dominant over time. Another possibility is that dark energy results from a new, unknown quantum field, dubbed quintessence. Unlike the cosmological constant, this field could vary over time and space, opening the door to even more complex scenarios. Perhaps the acceleration of expansion is not constant. Perhaps it fluctuates, intensifies, or even reverses. There are also bolder proposals suggesting that the laws of gravity might be different on cosmic scales, and that dark energy is actually a reflection of a physics we do not yet understand. In any case, it remains the greatest enigma in contemporary cosmology. Measuring dark energy requires observing the universe on the largest scales. Observations of the cosmic microwave background, the distribution of galaxies, gravitational lensing, and the acoustic oscillations of primordial plasma help scientists map how the universe has expanded over time. Each data point, each new measurement, helps refine the cosmological model we use to describe the cosmos. And so far, all this evidence converges toward a single conclusion. Dark energy is there, acting as an invisible thrust that dilutes everything toward the unknown. The presence of dark energy also raises profound philosophical questions. If it continues to dominate the universe, the future will be one of infinite expansion, of absolute isolation, of the great silence. Galaxies will move away at such extreme speeds that they will vanish from view. Stars will cease to form. The universe will become dark, cold and empty, not through destruction but through separation. Dark energy, then, doesn't just transform physics. It imposes a new kind of cosmic loneliness, where every point in space irreversibly distances itself from all others. To contemplate dark energy is to realize that the universe is vaster, stranger, and more subtle than we ever imagined. A force we cannot see, yet one that defines the rhythm of everything. It shapes the fate of galaxies, but also of time, light, and thought. Even without fully understanding it, we already know we live in a cosmos governed by something invisible, a serene and immense force that silently writes the final chapter of universal history. And perhaps the most astonishing truth is this, that amidst the chaos of stars, the dance of particles, and the order of physical laws, the entire universe is being carried, gently, by the invisible current of what we do not yet know. If the universe had a defined beginning, the Big Bang, it's only natural to ask, how will it end? This question, as ancient as philosophy and as profound as modern physics, leads us to three major scenarios describing the possible ultimate fates of the cosmos: the Big Freeze, the Big Crunch, and the Big Rip. Each represents not only a scientific hypothesis, but also a reflection on the nature of time, matter, and existence itself. These are futures calculated based on current physical laws, yet still wrapped in uncertainty, because what's at stake isn't just how the universe ends, but how it chooses to persist or disappear. The Big Freeze is the most widely accepted model based on current observations. In it, dark energy continues to drive the expansion of the universe indefinitely. Galaxies move so far apart that the light they emit will never reach Earth or any other point. The sky will grow increasingly dark. Star formation will cease as interstellar hydrogen becomes scarce. Existing stars, one by one, will exhaust their fuel and go dark. Only white dwarfs, black holes, and scattered particles will remain in a sea of thermal darkness. Over immense timescales, even black holes will slowly evaporate via Hawking radiation, and all that will remain is a cold, silent vastness, near absolute zero, with no light, no heat, no structure. The Big Crunch, on the other hand, proposes the opposite, that gravity in the long run will overcome expansion. In this scenario, dark energy would weaken or change its behavior, allowing the matter in the universe to regroup. Expansion would halt, and the cosmos would begin to collapse inward. Galaxies would draw closer, cosmic collisions would multiply, and the average temperature would rise again. Time, in a symbolic sense, would reverse, everything returning to a state of total compression, until the entire universe is concentrated in a single point of infinite density, a new zero point. For some physicists, this wouldn't be the end, but the start of a new cycle, a big bounce where each universe dies and is reborn eternally, like an infinite cosmic heartbeat. The most dramatic of the three scenarios is the Big Rip. Here, dark energy not only continues to accelerate the universe, but does so at an increasing rate, becoming so intense that it begins to tear apart gravitational and atomic bonds. Galaxies would disintegrate first, then stellar systems would be pulled apart. Eventually, even planets, molecules, and atoms would unravel under the extreme stretching of space-time. Finally, the very fabric of space-time would rip apart in a process that would destroy everything: matter, energy, and physical laws. Time itself would lose meaning. It would be an absolute end, but not just of existence, but of the very concept of reality. It's impossible to say with certainty which of these futures will occur. Everything depends on the true nature of dark energy, the total mass of the universe, and parameters not yet fully understood. What we do know is that we live in a privileged era between the birth of stars and the final darkness, between the primordial silence and the silence still to come. We are witnesses to a universe still vibrant, still luminous, still fertile with galaxies and possibilities, and that in itself is already extraordinary. To think about the end of the universe is not just a scientific exercise, but also a philosophical dive into the meaning of existence itself. If everything is destined to vanish, what is the value of life, of consciousness, of memory? Perhaps the answer lies in the very fact that even with an inevitable end, the universe managed to produce complexity, beauty, and thought. It was capable, for a fleeting moment, of looking at itself and asking questions, whether through freezing, collapse, or rupture. The ultimate fate of the cosmos will, in the end, be an extension of the mystery that gave it birth. And in this interval between the Big Bang and the final breath, we are the universe's breath, brief, aware, and full of meaning. In a future so distant that numbers themselves lose their human meaning, everything we know today as matter, planets, stars, bodies, objects, thoughts, will have been transformed into solitary particles, adrift in a void without color, without heat, and without horizon. This is the time of the last atom, a concept representing the absolute end of structured matter in the universe. It marks the point where there are no more chemical bonds, no fusion, no clumping gravity. Only subatomic particles, perhaps lingering protons or photons, stretched into infinity, drifting through a cosmos that has lost its rhythm, its structure, and its purpose. If the Big Freeze scenario proves true, the timeline that separates us from this final moment is nearly inconceivable. In about 10 to the power of 14 years, the last stars will have died. The universe will be populated only by white dwarfs, neutron stars, and black holes. Between 10 to the power of 30 years and 10 to the power of 40 years, even the remaining planets will be torn apart by gravitational interactions or consumed by black holes. But the end of matter will still not have arrived. Protons, the fundamental building blocks of atomic nuclei, are stable, but perhaps not eternally. If proton decay does occur, as some particle physics theories predict, then atoms will gradually vanish, converting into faint radiation and inert fragments. This epoch is known as the degenerate era. Usable energy becomes scarce. The universe no longer forms new systems, no longer births stars, no longer fuels chemical reactions. It is a universe where entropy has reached its peak. Heat, once distributed in gradients, is now evenly spread. Nothing is hotter or colder than anything else. Time continues to pass, but there are no longer events to mark its flow. The passage of time, so essential to human experience, becomes an abstraction devoid of change. The cosmos enters a state of perpetual silence, where everything remains but nothing ever happens. Even black holes, massive and mysterious as they are not eternal. According to Stephen Hawking's theory, they slowly emit energy through a phenomenon known as Hawking radiation. Over 10 to 100 years or more, black holes will gradually lose mass until they evaporate entirely, leaving behind only background radiation. When the final black hole has dissolved, no structure will remain, only isolated particles and diffuse radiation. This is the true endpoint of matter's story. No new star will ever ignite, no new atom will ever be formed. The universe will have returned to a state even more sparse and silent than the dark age following the Big Bang. And yet, even in this terminal phase, the universe continues to expand. Space keeps growing, carrying the last particles farther apart, separating them until physical interaction becomes impossible. Matter becomes memory. Light becomes a stretched-out echo. Gravity becomes a faded trace. Everything dilutes into a borderless vastness, where the very definition of existence frays until it becomes indistinguishable from nothingness. At this stage, time loses its direction, and the universe in its entirety dissolves, without drama, without explosion, without abrupt end, merely fading like the final ember of an ancient fire. To contemplate the last atom is to confront the deepest notion of finitude, not just the end of life, but the end of structure, of form, of matter itself. It is a farewell without witnesses, without return, and yet this distant and somber future highlights the preciousness of the now. Because between the Big Bang and the final dispersion, there was a moment, this moment, when matter organized itself, shone, thought, created art, science, music, and love. There was an instant when the universe knew it existed, because one of its fragments became conscious, and perhaps that, even if only for a few billion years, was the apex of complexity and the miracle that nature will never repeat. As we contemplate the universe, even with the most powerful telescopes ever built, we are always looking from within. Within time, within space, within the expanding bubble that began with the Big Bang. And this leads us to one of the most provocative questions of all. Is there something outside the universe? What lies beyond the edge of observable reality? The answer, as fascinating as it is not simple, and may not even be fully accessible to human logic, because the universe, in its birth and structure, is not expanding into something larger. It expands space itself in all directions. Even so, bold theories try to imagine what could exist beyond the cosmic boundary. Let us begin with what we know. The observable universe is about to take 93 billion light-years in diameter, a limit defined not by the actual size of the universe, but by the light that has had time to reach us since the Big Bang. This means that there may be, and very likely is, more universe beyond what we can see. Regions so distant that their light has yet to reach us. These areas might contain more galaxies, more stars, more cosmic structures, or perhaps different variations in physical laws, fundamental constants, or even elementary particles. The universe, therefore, could be immeasurably larger than anything we've ever observed or imagined. But there are even more radical hypotheses. One of the most discussed is that of the multiverse. In this idea, our universe would be only one among countless cosmic bubbles, each with its own physical laws, constants, and histories. These universes could exist within a deeper space, a hyperspace of quantum possibilities, where constant energy fluctuations give rise to new universes like bubbles forming and expanding in a boiling liquid. Each bubble could contain different amounts of matter, different geometries, even different dimensions. In some, stars may never have formed. In others, the very notion of time might be unrecognizable. Another possibility is that the universe isn't curved or finite, but without borders, like the surface of a sphere in 3 dimensions. In this vision, if you traveled in a straight line for long enough, you would eventually return to your starting point. The universe would have no outside, but instead a closed topology, where space and time fold upon themselves. This cyclical geometry forces us to abandon the idea of physical boundaries, replacing it with a notion of finiteness without edges, something deeply counterintuitive to the human mind, which is used to beginnings, middles, and ends. And what if the universe we know is merely a 3-dimensional projection of something larger and more fundamental? Some interpretations of theoretical physics, such as the holographic principle, suggest that everything we see may be a coding of information inscribed in a lower dimension, like a hologram. This would imply that the true universe lies outside the dimension we perceive, in a deeper plane where space, time, and even consciousness are projections. It's still a speculative idea, but it arises naturally in certain versions of string theory and quantum gravity. In the end, what lies outside the known universe may not be a place, but a question. The boundary may not lie at the edge of the cosmos, but at the limits of human understanding. Every scientific advancement pushes that limit a little farther, revealing new layers of mystery. Still, the very existence of an observable boundary reminds us of our position. Small, curious, conscious, trapped within the bubble of time and light, yet daring to imagine what lies beyond. And perhaps that is the most extraordinary thing, that in a universe where all things tend towards silence, there was a brief moment when matter organized into eyes that observe, into brains that inquire, into voices that narrate. And those voices, made of carbon and memory, dared to ask, what if there is more? What if something lies beyond? Because the greatest boundary may not be in space, but in the capacity to dream of what we cannot yet see.